So we'll just jump in. So my name is Joe Insley. I'm the lead for vision analysis at the ALCF. And of course, you just heard from Mike, and Silvio and I are going to kind of tag team this intro section to give you an overview of visualization. So here's a plan for the next hour or so, or 52 minutes that I have left. So we'll start. I'll show some examples of visualizations of some things that were done on our systems from data that was generated on our resources at LCF. Talk a little bit about visualization resources. I know you've been using Cooley a little bit, probably not for doing visualization, but for doing some other stuff this week, because I've seen some jobs running there. Talk a little bit about different visualization tools and data formats. Spend a chunk of the next bit of time talking about different types of data representations, different representations, visual representations for your data. A little bit about beyond just using visualization as the end product for looking at, trying to get insight into your data, but also using visualization as a way of debugging and perhaps doing some profiling of your code, that sort of thing. Just a couple short examples of that. And then at that point, I'm going to turn it over to Silvio to talk a little bit more about in situ visualization and analysis. So as the resources continue to get bigger, one of the biggest bottlenecks is writing data to disk. And so there's been a lot of work in the space of looking at how to do visualization and analysis on the data while it's still in memory on the big resource. So Silvio's going to talk a little bit about that. Some of the things that I'm going to talk about next are sort of more traditionally have been used for doing post-processing of data, but we're now starting to look at doing the same sorts of things again in situ while the simulation codes are still running. So a couple examples of different types of visualizations that we've worked with, a couple of different projects. So this is an example of multi-scale simulation and visualization. It's a team that's looking at arterial blood flow. And so what we're looking at here is these are arteries in the brain. And in particular, they're interested in understanding what's happening in this aneurysm. You see this sort of bubble that's formed on one of the arteries. And so they're interested in understanding what's happening in this, how the overall blood flow in these arteries impact particle buildup on the wall of this aneurysm that could cause this essentially the aneurysm to burst or for it to this clot to break free and cause obstructions. And so the simulation itself is a coupled code. So they run a fluid dynamics that's doing the overall flow, and then a particle dynamics that's looking at data in this little subregion here where there's these particles that are building up on the wall of the aneurysm. And to give you an idea of the scale, this actually was a code that ran a couple of years ago, but it ran the fluid dynamics code that does the overall flow in the arteries ran on one rack of the supercomputer, and the particle dynamics that's calculating the particles in this small subregion ran on 31 racks, right? And so obviously there's no way to do this level of detail throughout the entire system. There's just not enough compute for that. So that's one of the important reasons why it's important to be able to couple these two different scaled codes, and they can talk to each other. So the overall flow impacts the positions of the particles, and then in turn, those particles impact how the flow can move through that domain. And then there's similar challenges when looking at visualizing data that's at these two very different scales. This is an example of climate. I'm not going to spend too much time on this. I'll just say that this was another example where it was a coupling of a lot of different climate models, and they started with observed data, right? And so they took this observed data, plugged those in as the initial conditions for their simulations, and then simulated forward, and were able to then go back and compare, how do their models compare to the actual observed data, make improvements on their models based on that, et cetera. In addition to, most of the teams that we work with that use our resources, a lot of them are from other national labs or academia. We do also have a number of corporate partners. So this is an example of GE, who engineer and produce jet engines. And so they're also using our compute facilities at the ALCF. This particular one, they're looking at reducing noise emissions from jet nozzles, which also, in addition to cutting down on noise pollution, could also lead to better fuel efficiency. And so this is an example of that. Lots of different molecular and material science projects that use our resources. John will talk a little bit more about VMD and molecular dynamics type visualizations this afternoon. We also spent a fair amount of time working with the hack team that does different cosmology simulations. So this is an example of that, using VL3, which is our code for doing volume rendering. And we'll actually play with a little example of that this afternoon when we look at playing around with the Jupyter notebooks. So a little bit about resources. So by now, you're probably familiar with Cooley. Again, we primarily use it for doing visualization and analysis. That's its intended purpose. 126 nodes. Each node, as you probably know by now, has a couple of 6 core processors, NVIDIA high-end graphics cards in it. And one of the major things is that it has lots of memory. So each node has 384 gigs of RAM. And then one of the key points of this slide is just that it also mounts the same shared file system as Mira and Cetus, our supercomputers. Actually now also shares a file system with Theta, our other main resource. And so again, when we're doing post-processing of data, this enables us to be able to access data from the same file systems and not have to move it around. Like a lot of our many users, we're producing these large piles of data. It's not convenient or even in some cases possible to move all that data back to their home institution. So they leverage Cooley for doing visualization and analysis. And more we're starting to leverage also Theta for doing that as well. And that's going to start playing a bigger role as we move into some of the in situ stuff that Silvio will talk about in a little bit. So a little bit about some tools and different data formats. So there's all sorts of tools out there for doing visualization in this space. There's a number of open source applications that are intended for doing large-scale parallel visualization. Visit and ParaView are a couple of the primary examples. And again, we have representatives from those teams here that are going to do some hands-on stuff with us today. Insight is actually a commercial product, so we don't use it very widely, but it's another similar product that's out there. Lots of domain-specific tools. In particular, there's a handful. VMD, Megamol, Vito are some popular ones for doing molecular dynamics type simulations, visualizations rather. And I mentioned, the Visit and ParaView ones are more in the application space, and then VTK and ITK are programming frameworks and libraries that are used for building applications, and some of these other applications like Visit and ParaView are largely built on top of those APIs. There's some like VL3, which is our shader-based volume rendering and particle rendering application, uses leverages hardware. So it does leverages the GPU for doing rendering. Different analysis environments and utilities like GNU Plot and ImageMagick are, just a few of the tools that are out there for doing this, manipulating data and the products that they produce. And we'll talk a little bit more about that in a second. So I mentioned Visit and PairView. They're general purpose visualization applications. And so they're GUI based. And so they're good for doing lots of different types of visualization, as opposed to things more like some of the other ones that are more specific domain. They're largely GUI based. They have a client server model in order to support remote visualization. So the way we generally use it on our resources is you run a server, often in parallel on Cooley, the visualization cluster, and then you connect to that from a local client on your local resource, your laptop or workstation. So all the heavy lifting can happen on the big resource where the data lives, and then you essentially can interact with it in real time and do, depending on the scale of the data, it's either largely done remotely on the cluster and then ship pixels to your local client. Both Visit and PairView are scriptable and extendable, and so you can write plugins and readers and that sort of thing for each of them. Which also, the scriptable part also enables you to run them in batch. So often the way we work with those tools is to use them interactively to set up our pipeline, and then once we've established, okay, this is the visualization we want, we can then submit a batch job to render an animation, for example, and do that over a large number of time steps. Again, they're both largely built on top of VTK, and they both have in situ capabilities, again, that Silvio's going to talk about in a little bit. VTK, as I mentioned, is more of a programming environment, API. It has additional capabilities, and there's some finer control that it allows. Has somewhat of a smaller footprint, but it requires more expertise, right? So you end up building your own applications, or again, you can write your own plugins and ways of extending these other applications if they don't have some of the specific capabilities that you need. Lots of data formats. This is by no means an exhaustive list. Excuse me, but just to give you an idea of some of the different things that are available. And so chances are, whatever format that you're generating from your simulation applications, there's likely a reader for it. And there's also, for example, for HDF5, there's a format called XDMF, which is basically an XML wrapper around HDF5 that will help explain, and XDMF is listed there, basically helps define what's in your HDF data sets in order to enable the visualization applications to understand and read them. Let's see. All right, so at this point I'll jump into, so here's some of the different types of representations that we often use for representing data. So these are examples of volume rendering, which are basically, you have a volume of 3D volume of data values, and you assign different colors and transparency values to each of the values and the ranges of your data. And you basically look up those values in the table and assign values, colors and transparencies to those values. So for example, in our little mouse friend up here, we know that there's a specific range of values in this density X-ray data that's certain range of values that represents bone, different set of values that represents muscle or other tissue types. And so then you can color the color and set transparency levels for those different materials based on their values. Glyphs are basically 2D or 3D geometric objects that represents point data, right? So the location is dictated by the coordinate of the particle or the data point. So its location in 3D on a mesh, or position in a graph or table, for example, if you're looking at 2D data. And then the other attributes of the data are that you assign different graphical attributes based on attributes of the data. So for example, color and size and orientation. So in these examples up here, for example, the one on the lower left, there's some arrows there, and they're scaled by different sizes based on velocity, and the direction they're pointing is based on the vector of the orientation of the vector that it's pointing. Similarly, in this middle example, they're colored by their velocity. So slower particles in this case, this is looking down a tube of particles that are moving through a tube, and the ones that are on the outside are moving slower, the ones in the center are moving faster. And then again, based on attributes, you can say color them by different types, like in that final example on the right there. So contours or isosurfaces, a line in 2D or a surface in 3D basically represents a constant value across a domain. So these are, Visit and Pair View have capabilities for doing this sort of thing. Again, they also have capabilities for the volume rendering stuff. VTK also has these capabilities, but again, that requires a little bit more effort. And so in this case, again, the surface represents some constant value through the domain, but then you can also color them by some other variable in that space. So for example, this example down here from the jet, the ISO value is based on one variable, and the colors of that surface are based on another variable. Cutting planes are basically what they sound like. It's just a slice or plane that cuts through the data set and has basically colors it by the value of the variable that you're looking at. Again, Visit and Pair View very good at this. It's a pretty common representation. Streamlines are basically, it requires a vector field on a mesh, so it needs connectivity. And so this is looking at showing the direction that an element's going to travel at any given point in time. So it's looking at the path it would take within a single time step. So you take a bunch of seed points in your domain and trace the path that those would take from one grid point to the next, and show the path that particles in that space would take. So for example, again, to use the example of the aneurysm, you have this flow that's coming in and swirling through that structure. So there's, as I mentioned, Visit and Pair View are these general purpose visualization tools. So they're often used for lots of different science domains, different types of representations, like the ones that I've showed. There's other tools that are geared more towards specific domains. So VMD, for example, is really good. It's designed for doing molecular dynamics type visualizations, and it has a lot of domain-specific types of representations. it, again, supports many different file formats and has animation and scripting capabilities. John will talk a lot more about that this afternoon. In terms of molecular dynamics, specifically Visit and ParaView have some support for this, and it's actually improving some of those capabilities. And again, VTK, anything's possible if you try hard enough. Those are tools that you have to do a lot of the lifting yourself using VTK directly. So a couple more quick things here. So again, just a couple examples of looking at different ways of using visualization. So not just as your end product, but for example, for debugging. So this is an example of, I was working with a team that was doing this fluid flow, and this, what we're looking at here is these are two propellers, and the one on the right is the one in the front, and they're gonna rotate in opposite directions. And so this team was, and it's a marine propeller, so there's a fluid that's flowing through here. And when they were doing the simulation, they were getting results that they weren't expecting. They couldn't understand why, and so they asked me if I would help visualize it and see if they can figure out what was going wrong. And so keep your eye on the propeller on the right, right? So as the simulation goes on, something happened, right? I mean, they discovered that, right, the propeller disappeared. There was something wrong in their code that was not reinitializing some value somewhere, and so that's why they were getting these, these whacked out results they weren't expecting. But so by doing some visualization, we were able to understand, oh, we need to go back and look at the code and figure out what, where we went wrong. Once they did that, this is the result they were expecting. You can kind of see sort of inside. This is I forget the value we're looking at here, but some surfaces. You can see this white sort of in the middle there. You can see the propeller sort of underneath these structures. And so these big vortex structures is what they were expecting to see. And without that first propeller, they were not seeing that. And so this is an example of using visualization for diagnostics, for example. So I mentioned our volume rendering code that looks at, that we use for doing large-scale visualization. And this is an example looking at some cosmology data. And we were trying to improve some performance by threading it, right? And we weren't quite getting the performance we were expecting. And so to try and get a better understanding of what was actually happening in the code, right? So here's a case where normally what the code does is it looks up for each particle in the volume, looks up its value in the data set and then colors it according to the value in the data. But instead what we did was, instead of coloring it by that, we colored it by the thread ID of the thread that was working on that part of data. And so you can see in the 4 different arrangements here, we played around with different ways of organizing the memory for the ways of assigning threads to parts of the data. And so this gave us some insight into how the performance was, what was happening in the performance because of how memory was laid out. And so those are just a couple examples of how you could potentially use visualization other than just the pretty pictures at the end, which hopefully give you some insight, but also using it for informing you about how your code is running or help you find anomalies in the code itself.
So in this picture, the bottom left one is the good?
Not necessarily. It was, to be honest, I don't remember which one gave us the best performance. But by arranging you can see that the layout of threads per memory is very different in these 4 different examples. And with that, I'm going to turn it over to Silvio, who's going to tell us more about some of the in situ visualization analysis stuff that I mentioned.
All right. Okay, we have audio. So, hi everyone. I'm Silvio Rizzi, computer scientist at the Argonne Leadership Computing Facility, and I had the chance of meeting you last Saturday during the tour, most of you, right? So, we'll be talking about in situ visualization and analysis. And essentially, what's the motivation for this? So traditionally, science teams will run their large-scale simulations on the big machines. They will dump lots of data, and they will postpone the analysis to a later time, right? Sometimes that may take months or even years, right? And there's a big constraint there. When dumping simulation data to a file system, you're limited by the storage, right? By the storage amount you have available. And you're also limited by the I/O, by the transfer rates, right? Or bandwidths. So our community noticed that a few years ago, that specific problems. And one of those specific problems is that due to the limitations of storage, right, you're forced to dump, you can't dump the totality of your time steps, right? You're forced to dump one every 10 or something like that. So if there's a phenomenon that you're looking for and it's happening in those 9 time steps that you dropped, you will miss it, okay? So there's potential lost science because of this thing. Because of these issues. So that's what the community recognized a few years ago. And we proposed what is called in situ visualization and analysis. So the idea is that you do the visualization and analysis while the simulation is running. The data is in memory. The simulation can share the data with your analysis or visualization code, and there's no lost science, hopefully, right? So you have access, the analysis algorithms will have access to the entire data set while the data set is in memory. So with that, we're solving two different problems, right? The problem about dumping a subset of the simulation data, and the problem of I/O. Of I/O limitations or bandwidth limitations. And this, we expect the problem, so the gap between flops that will continue increasing. In fact, in Argonne, we expect to be the first site to have an exascale computer. So think about a factor of 50 in terms of flops compared to what we have on the machines that you're using now, right? But the I/O is not going to increase like that. So the gap is increasing. So we need to do something. So that's the proposal. It's about doing in situ analysis and visualization, essentially accessing the data while it's still in memory. For that, we try to leverage existing platforms. So these codes that you see here are essentially codes that are in production, are running at scale, well-known, well-maintained. They have strong teams maintaining them. So one of them is Catalyst. It's a subset of ParaView, and it's specifically designed to run in situ. Same thing for LiveSim and Visit. Again, it works as a library, and it can solve this in situ issues. And finally, Adios. This is mostly an interface for moving data. Everything is files for Adios, so you can either write files if you would like, or move data to different resources. So the proposal is to leverage these existing platforms. Uh, our project, so we're part of a project funded by DOE called Sensei, and that's essentially what we're trying to do. We want to define an interface, and we want to use this existing infrastructures that are really good, actually. But the idea is to, if we use them, if we create a good interface, we will be able to use any of these infrastructures, right? And write the code once and use it multiple times. And actually, we will show some of this in the session in the afternoon, right? We'll have some nice toy examples for you to try this specific approaches. So how does it work? There is an application, right? In this case, it is a mini app, a well-known mini app, but this is what the original application code will look like, or the simulation code will look like, right? On this other side, there is the existing analysis, something that you know you want to do with the data. So the Sensei interface is actually providing this block here. It's got three main components: a bridge, a data adapter, and an analysis adapter, right? So the data adapter is actually going to get pointers to the simulation data, and it will pass them to the other side. And in this case, it's worth mentioning something important. We are using VTK because everything, all the infrastructures here are built on VTK. And VTK has mechanisms for zero copy, right? So we want to avoid copying, right? We want to avoid replication of data because we'll be running on the same resources where the simulation is actually running. So we don't want to duplicate the data. We want to access it while it's available, but not duplicate it. And once the data is in this format, is represented in this format that all the analysis will understand, there is an analysis adapter for every specific adapter. In this specific case, we are using Catalyst, and Catalyst is connecting to a ParaView server that also runs on the supercomputer resource. In this case, the video I'm going to show, this was an experiment on Theta, our machine at ALCF. Now, ParaView server runs on the machine, on the big machine, but you also want to access the data through an interface. So you can use the ParaView client, and actually you will use it today. And if you run the ParaView client on your local resource, you connect to the network to ParaView server and can interact with the data while the simulation is running. And you can see what's actually going on there. So imagine that. So many times science teams will need to prepare their large simulations, right? So they start with something smaller. They need to set the initial conditions right, okay? So if we do this, we can enable them to explore the initial conditions they have set. If things are not working as expected, they could just stop that simulation and start over and avoid burning lots of core hours, right? So that's a potential advantage too. So I have a video here from our KidWork folks showing specifically that, right? So the simulation is running on Theta, and you can see that this is the ParaView interface. It is connected to Theta, and this is running locally in a laptop. And now we're grabbing data from the simulation, right? So the analyst can run this interface locally and start querying the data and extracting data. So in this case, we can create extracts of the data and save to disk only the parts that are interesting. Or we can find specific regions of interest and save only that to disk. So with that, we can avoid the I/O bottleneck, right? So that's a specific case. We can also test initial conditions and all kind of possibilities here, right? Yes? Yes, so the question is if the visualization and analysis will run on the same resources. And yes, that is what we know as proper in situ, right? So you need to allocate some memory and resources for the analysis and visualization on the same nodes. And there's an alternative that we call it in transit. In transit means that you copy the data and move it to another resource. It could be a partition of your supercomputer, some subset of nodes on the same supercomputer, or it could be a different resource. Like, for example, in ALCF, we have Mira connected or sharing actually the file system and interconnect with Cooley. So we could be doing in transit there, like running the simulation on Mira, shipping the data to Cooley for analysis and best. Okay, so there's those two cases, in situ and in transit.
Do I need to change my application code?
I'm sorry, say that again?
Do I need to change my own code to be able to use this?
Yes, you need to change your code, but minimally. The idea is to not interfering with the original code. So you need to add some calls there. And let me go back to this diagram here. So there's essentially 3 calls that you will need to do from your application to talk to Sensei or most of other in situ solutions or infrastructures. One for initialization, where you pass your MPI global communicator to the other side, right, to the analysis side, because they will need it. One call every time step to update the data, and one call to finalize, right? When you're going to finalize MPI, before doing that, you call and let know the simulation side, the visualization and analysis side that you will be finalizing. Yes?
So you're visualizing as the simulation's happening, so does that mean you're restricted to making just the time step that's currently being worked on?
Right. In this case, you are accessing the time step that is current at the time. But nothing prevents you from actually collecting multiple time steps on the analysis side and do a multi-step analysis, right? Yes. Any other questions? Yes.
So, I was wondering how the data is being shared between the simulation and the visualization. I mean, is it a file system? Because if that's the case, then it's not truly in situ in some sense, right? I mean, it's not in memory.
It is in memory when we're sharing it in the in situ case. Yes, it is in memory. Okay. Right.
That means data has to be collected from all the processes that are running onto a single node to
It depends on how you set up the analysis, right? And in some cases, you may want to have one simulation rank with one associated to one analysis rank, so they will run on the same node. In other cases, you want an M-to-N communication pattern, specifically in transit, right? When we are going to move data or ship data to a different number of nodes, you may have a smaller number of nodes dedicated to the visualization and analysis. Yes. Cool. Yes.
I'm just curious about how you make, under the hood, how you make the in-memory access possible. Do you use a POSIX shared memory mechanism, or?
No, actually, you pass pointers. You pass pointers to memory, and that's what you give to VTK. And VTK uses actually a zero copy mechanism to create internal representations of arrays, and that's what you pass to the other side that is essentially enabled to understand that. Okay? All right, let's move on. So this is an example, a specific example of Osprey in situ for interactive visualization. And Osprey, let me actually introduce it properly. It is an environment from Intel optimized for CPUs, right? Since our current supercomputer Theta is CPU based, and it uses actually Intel CPUs, it is actually a perfect resource to deploy something like Osprey. This is actually a ray tracer, highly optimized for Intel CPUs and Intel architectures. They can do pretty much everything a ray tracer can do. And this actually, I borrowed this slide from the Intel Fox. Lots of different visualization techniques available there. So Osprey is available online. You can download it, build it, and try it on your own computers. And we're working closely with this team because this is something we want to enable. And actually, we have enabled it already. We have material science, or lots of material science use cases that use a code like LAMPS for molecular dynamics. And it was mentioned that this code has been mentioned many times. So we want to visualize interactively the data coming from this specific simulations. So this is our solution, right? We drive LAMPS, the simulation code, externally, so we need to build it as a library, and we drive it ourselves. So we get the input file directly from our file and pass it line by line to LAMPS. So with that, every time step, every new time step of data computed by LAMPS, it's shared through this, let's say, interface here. So we have a data adapter there, our bridge, and multiple analysis adapters already available in Sensei. In our case, we created one specific adapter to talk directly to Osprey, pass the particles coming from the simulation to Osprey, the ray tracer. And in that case, we can interactively visualize the data as it's being simulated. And I have a video for that, demonstrating that. Hope it's playing. So, 2 terminals here. On the top, we launch the driver running LAMPS. So this is actually the LAMPS output. And this is the client, right? The Osprey client receiving the data and now launching the interactive viewer. So the data is actually live. And you can see it here, how it changes with every time step. There will be some atoms popping up. And you can see the simulation keeps going and making its data available, and we ray trace it in Osprey there. So we can explore the data while it's actually being computed. Okay, that's the main idea here for this specific work. But you could be doing analysis, or you could be saving images to disk. I mean, there's lots of possibilities here. So with that, we conclude the presentation, the material we had for this morning. In the afternoon, we'll be poking at some of these concepts with Jupyter notebooks. And we'll be happy to take any questions you may have now.